All right, so we're going to get started. So welcome back. This is the last session of this morning. So we are going to hear from Jonathan Hodges. Jonathan is worked, for those of you who know him, worked with Brian Latimer during his PhD, and he's right now a consulting engineer at Jensen Hughes, and he's going to talk about other types of application of technology and looking at fire forecasting. Jonathan, the floor is yours.
Thank you, Arno. So once again, my name is Jonathan Hodges. I'm with Jensen Hughes. Just a little bit of background about me. So I'm in charge of modeling within our research and development division at Jensen Hughes. So I do some development work with NIST on fire dynamics simulator, and I manage technical quality across the commercial and research projects that we do using modeling kind of across the company. Today, we're going to talk about, I changed the name to faster than real-time fire modeling because you don't really care if your model's real-time. It needs to be faster than real-time in order to provide a forecast for decision-making. Just a little bit of information about Jensen Hughes. We're the largest fire consulting firm in the United States, one of the largest in the world. We have offices in 90 different locations worldwide. We serve on just about every NFPA committee, not all of them, but close to 300 or so. And we do a lot of publishing, a lot of research. And so we've got several in-house laboratories, and our tagline has always been advancing the science of safety. And so that's what we try and bring to the consulting environment. So I'll stop the sales pitch and get into what we're here to talk about. So 5 main topics. We'll start with some background on data science. We won't talk too much about fire forecasting background since you guys have already gotten that this week from other lecturers, but I'll mention a few points that are relevant to this topic. And then I'll talk about different approaches that people are using to improve fire forecasting. Because as we've talked about this week, there's a lot of issues with the operational tools that are available. Then we'll end on some emerging concepts of new work that's not really been seen a lot in practice, but people are starting to publish on. All right, so we'll talk about some data science topics. So I'm throwing up as many buzzwords as we can right here. So we're just going to define our terms to start off. Artificial intelligence is when you are actually dealing with decision making. So some model or software is replacing the human or telling the human how to make the decision. That's actually making the decision. Machine learning is a statistical tool that is used to have an algorithm learn coefficients and such from data. So it's a modeling type term. It's not making decisions, but it's just making a prediction. Deep learning is a subset of machine learning where you're dealing with models that are too complicated to really understand why they're making the decision that they're making. And then the last term here, sorry it's not in the graphic, is data assimilation. This is a tool where you're fusing information from a model, could be a machine learning model or a physics-based model, and observational data. So the key difference there is that you're using data from a specific event to improve your understanding of what's going on in that same event. So lots of different types of data. If we're just talking about the structure of a specific data point, there's 2 main types. It can either be a categorical data or it can be numerical. Within categorical data, you have 2 types. One where the ordering of it matters. Think about a test grade. In general, an A is better than a B is better than a C is better than a D, for example. You also have nominal or not ordered data. This is, the classes don't really mean anything, they're just different. So we've got cats, dogs, camels, things like that. When you look at wildfire models, you have the fuel model, which you would think the number might correspond to an increasing rate of spread or something. They would be ordinal, but that's actually not ordinal. They're categorized by like grass type, shrub type, slash, things like that. And so the number itself doesn't actually give you a great insight into the rate of spread calculation. So you have to be kind of careful, because even if you have a numeric value, it might not actually be an ordinal data set. On the other side, you have numerical data. 2 main types, one being things you can't divide. So usually this is integers, so number of occupants in a building, number of evacuees, number of firefighters, things like that. Another is continuous data, which can be divided. So wind speed, any sort of number. You also have the different types of topology in the data. Two main types. You have structured data that has some regular grid to it, some geo-coordinate that's internally consistent. So within that set, you can have vector data dealing with like county lines, fire perimeters, for example, level set solutions, all of that. You can also deal with raster data. So if you're working with land fire data, for example, it's typically put out on a grid. I guess 30 meter for most data sets, might go down to 15 for some of them. And that's all, think of like pixels in an image, a raster. But you also have unstructured data. And this happens a lot when you have drones flying over, for example. They're following some path, and that path is usually not going to be the same in any individual fire or any individual patrol, unless your control systems are super good, which they probably aren't. You also have data that you can collect from the public. So this is usually called like volunteer geographic information. And so here we're showing some examples of Twitter posts that are mentioning fire or wildfire and looking for hot spots. Unstructured data has its own difficulties when you're trying to use that to inform real-time operations, because you don't really know where it is. You have to kind of tag it all. And especially if you're dealing with information from the public, you have the potential for incorrect information, either on purpose due to bad actors or due to just people saw an orange flag or an orange bus or something. They thought it was a fire and they reported it. And so it can mislead. So you have to be careful when dealing with that type of data. All right. So in a traditional modeling approach, you have some initial state, think initial conditions in your model, and then you have a model that is used to predict how that evolves in time. So initial state, prediction, next state estimate. The general premise of data assimilation, if it will go, all right, is to instead take your initial state estimate, then also take a measurement and fuse that information together to get your next state estimate. There's lots of different approaches to this, but that's the general concept, that your future state depends on your current state as well as data that you're collecting right now. When you're looking at data assimilation, you can also deal with an ensemble of states. And what this means, for example, you have a wildfire perimeter. You don't really know what your weather is going to do. So we're going to have some set of lots of weather profiles. We're going to propagate that fire perimeter with an ensemble using lots of different weather conditions. And then we have some observation, maybe due to drones, maybe due to people walking the line. But there's also uncertainty associated with the fire line that you've measured from whatever source. And so what you can do is take the state that you've estimated and fuse that together with that uncertain observation to reduce the overall uncertainty of your ensemble. And then you continue going forward in time with whatever parametric set that you're working with. All right. So formal definition of machine learning, and we'll talk about these terms a little bit more. A computer program is said to learn from experience with respect to some class of tasks if its performance is in these tasks as measured by whatever metric you're doing, improves with experience. We'll talk about what each of those different terms mean. There's roughly kind of 5 main tasks you can get to in machine learning. I promise this is relevant to wildfires. We'll get there, I promise. So classification, this is identifying the type of something. For example, if you have an image and you want to say, is this a firebrand or not? If they were talking about in the amberometer, for example. Clustering is an approach where you're saying, I've got all of this data, what things are similar? What are the logical groups? This type of analysis is used a lot in land fire and updating of fuel maps, because you're looking at your reflectance values, your ground observations of measurements, and coming up with some idea of how you should update these different models based on that statistical analysis. We also have regression. We're actually trying to estimate some specific number. So in the remote sensing talk, we're talking about measuring that radiant intensity, saying, well, how does that correlate to heat release rate, for example? You can also do anomaly detection, something like we've got all this data coming in from Twitter talking about wildfires, and there's a few that are really outliers. They don't look like they're real observations. And so there's tools you can use to identify those bad actors. And then the last is transcription. We're taking data and translating it into some other form. We won't talk about that much today. So when we're talking about experience, there's really 2 sets. The easiest to think of is what's called supervised learning. And what you're doing here is you're telling the computer, these are apples, these are oranges, these are birds, these are pears, whatever groups, telling it that. And then it's saying, okay, I'm going to look at these, identify the key features here, and I will tell you how I can describe these back to you. Unsupervised learning is the opposite. It goes back to that idea of clustering. We're saying, I'm just giving you a bunch of stuff, and I want you to group it. And then you tell me what types of groups you're seeing. So here you give it a basket of fruit, and it'll give you what types of fruits are in the basket. What type of fruit are in the basket. Performance metrics, there's lots of these out there. The example I'm showing here is in binary classification. It's probably the easiest to understand. You have a confusion matrix shown in the top right here. All correct predictions are on one of the diagonals. So here, say we're looking at whether you're getting an ignition or not. If it's correct, then it's in one corner. If it's correct, then there's no ignition. It's in the other corner. And then your off diagonals are showing you the errors in your predictions. So if you have a false positive, for example, this would be the fraction of false alarms that someone has to investigate to see if you actually had an ignition. Sending a drone out to look at, sending a utility worker to look at, or sending someone from the fire service and mobilizing. You also have what's called the other way around, a miss, where you say there's not an ignition, but there actually was. And in that case, the question is, well, is it an ignition that is going to be very risky? And so you have to consider these things when you're looking at your metrics, because what metric you choose when you're designing these models will really drive the performance of your model. You may need to bias your system to miss no ignitions, and then you're going to have a much higher false discovery rate because there's always a trade-off between your type 1 and type 2 errors. So this is a critical thing to consider when you're designing these types of models. All right. Then another thing that's important to understand with any data-driven model, not just machine learning, but also if you were fitting a poly data in Excel, you've got 6 data points, and you're trying to put a 5 exponential curve to it. You can go through every point very easily, very low error, but you get something that looks like that top right there, where you've clearly overfit to the model. In the machine learning space, what this is called is capacity. And so the model needs to have the correct amount of capacity to describe the phenomena well without overfitting. If you don't have enough capacity, then you don't have enough dimensions to your problem, and you end up with an underperforming model, like a linear fit when it's clearly a cubic or quadratic or whatever fit you have. You can also introduce something called regularization. This is where you're purposely making it harder on the model to learn so that it is forced to learn more robust features. All right. So artificial neural networks, they're my favorite. I did all my doctorate work was using neural networks. At a fundamental level, they're just massively parallel systems of equations. You have a generally linear form of a neuron shown there in the top right. The nonlinearity comes where you're remapping the output using what's called an activation function. When you're talking about a neural network, you have a bunch of these neurons that are interconnected together in some cohesive fashion. In general, when people are talking about deep learning, all they mean is they have at least 2 layers on the inside of their neural network. Because it gets very complicated there to understand what the decision's being made. All right. Last thing on the machine learning front is a convolutional neural network. These are, in a lot of ways, kind of the king of image processing or 2D topology when you're trying to do classification or predictions. And basically what you're doing here is taking your neurons and arranging them into what's called a filter. So it has some 2D or 3D or n-dimensional representation, kind of like a tensor. And then you're processing that filter along an image pixel by pixel. And the response of the image to that filter is what's called a feature response map. That is telling you the relative importance of each of those factors in making a decision. Reason that's important is even though you do get deep learning where it gets difficult to make decisions, there are tools that are available to you to help you understand how the decisions are being made and what features are important to individual decisions. But you can't just look at the raw output. You need to be looking at what's actually being done under the hood. All right. Now we'll talk about forecasting just a little bit. So there's lots of types of forecasting out there. The type that we're going to talk about today is when you're trying to actually predict the perimeter of the fire as it's going to be growing over time. So you have some evolution of the over time from some discrete point, and you're trying to predict that. You could also be looking at spot fires, etc., but it's for a specific scenario. And we're interested in this for public evacuation and prioritizing emergency response, either helping people evacuate, issuing the orders, or working on containment or suppression efforts. As the other speakers have talked about, there's really high uncertainties in all of these models. These are due to your current state. You don't really know what your vegetation or moisture is right now, uncertainty in what your actual fire perimeter is. There's also a lot of uncertainty in predicting the weather, especially when the fire starts to have that two-way interaction where it is affecting the weather. Lots of technologies exist in these forecasting. Most of them are empirical models. We've also talked a little bit about research-grade tools, and then we'll talk a little bit today about data-driven tools. All right. So in my schematic here, just showing the general process at a high level of a wildfire. You have some ignition, and it's not going to be detected immediately, usually. So there's some time associated with when you actually get the detection of the fire. Once you have the detection, emergency response starts. Might be just confirming that there is a fire, might be mobilizing, might be issuing evacuation orders. Typically at that same time, you're also getting ready to start your modeling. But there might also be some upkeep time, where it might take some time to actually set up your model configuration. So there's some lag there to start your simulation. Then it takes some time to have the simulation actually run to give you fire perimeters in the future. And so there is that delay there. Now, how long that delay is depends on lots of things: the quality of the model, what you're looking at, how long of a forecast you're looking for. Then the positive lead time is how long in the future you are predicting, minus the time it took you to get set up and running. All right. And unfortunately, fire is a very complicated phenomena, and wildfires are even more so. And because of that, there's no way to solve these things from first principles in a way that can support operations. So what we have to do, we have to simplify things. Typical tools that people are using empirical formulations for atmosphere, fire, and vegetation. You have these fast simulations, but high uncertainty in the predictions. Research-grade tools reduce this uncertainty typically by incorporating additional physics into the model in some way. Now, there's different ways to do this. The most popular that people have probably heard of is doing the physical atmospheric modeling, where you're coupling a weather model with the fire model, and you're looking at the fire, how the fire is affecting the growth profile of the weather, and that's then driving additional changes in your fire spread. But you can also look at other models where you're physically resolving the fire, saying, well, this wind profile is going to tilt the fire in a different way, which is now going to change our heat transfer to the fuel, and you can have some physical model for your vegetation so that you can be dynamically scaling that rate of spread based on that heat transfer. But in all of these approaches, they're a lot slower, hopefully lower uncertainty, not always, depends on the quality of what you're doing, but they're slow. So the question for today's talk is, how can we use modern technology to improve these models, to make accurate, faster than real-time simulation? All right. So 4 main approaches that we're going to talk about here, and some of them are related to improving the quality of existing models. So taking an empirical model, using Rothermos with just normal weather conditions, and understanding how can we improve that prediction. There's other tools in related to how can we scale up more or higher fidelity models and run them faster so that they can be used in fire forecasting. All right. So probably the most straightforward form of data assimilation is what's called reinitialization. This is the approach where we say, I have a fire perimeter, I'm going to forecast it until I get some observation of what the fire perimeter is, and I'm going to abandon my old model, and I'm going to start over with this new observation. Works pretty well. It limits the overall propagation of your error because you're resetting to a 0 within your uncertainty of knowing the fire perimeter, but some zero uncertainty in your model, and then propagating it. So it's limiting that propagation over time. But it doesn't actually really improve your forecast. It just resets you to zero to bound the error. Lots of different researchers have used these. Typically, when you're looking at these types of approaches, the metric that people are looking at is, this is a Sorensen coefficient, but it's saying basically, where do I have a fire that I'm supposed to, where do I have a fire that I don't, or that I'm not supposed to, and vice versa, and coming up with this kind of weighted average of those. And researchers have shown, as we expect, that if you're looking at a 12-hour forecast without reinitialization, that it is generally worse than a forecast when you do have reinitialization. But by definition, we're doing a correction every 12 hours, so empirically that makes sense. But this is probably the most commonly used tool in operational tools because it is easy. You have some observation, you reset it. So this is used all the time in wildfire modeling. Another approach is the filter-based approach. This goes to what we were talking about before, where you have some initial state, and then you have data, and you're fusing it together. So you're not directly updating your perimeter. You're using that information and fusing it to hopefully reduce your overall uncertainty. So there's been a lot of approaches presented for this. Sometimes they're in use, but it really just depends on the jurisdiction and what's going on. There's a lot of issues with data quality and making sure that you're automating this process. So it's still a fairly manual process in specifying the perimeters. But if you're specifying a perimeter for reinitialization, it's not too hard to then use that for data assimilation instead, because you've already got the perimeter. So lots of researchers have done this. A lot of it was done by Rochot here. I think or it's person's Melanie. Am I right on that or no? Melanie Rochot, is that right?
Melanie Rochot.
Yeah, there we go. I apologize. So a lot of this work has been done by her. And you have the fire perimeter shown here on the left, where this is the assimilation time step. So the blue is at a current state where we see this error. And then you have the black plus signs here that are showing the observation at this time step. The red profile is showing after data assimilation. So in this particular case, the model was tuned so that it was using the assimilated perimeter more so than it was using the forecast. And you can, based on how you design the model, you can weight it to use them, use one more than the other, et cetera. But what's interesting about this case in particular is that after doing the assimilation at the previous time step, the forecast going forward actually did a pretty good job at tracking the perimeter at the next time step, even though it hadn't yet been assimilated. So the thought here is that when you're assimilating and you're estimating the uncertainty in your forecast and in your observations, that by embedding that information, you can improve your forecast. It's been shown to work in some select cases, but this is usually done on pretty small fires. There's not really a broad validation basis for its use at the regional scales. When we're talking about data assimilation, both these approaches have the same kind of errors where you're limiting the overall propagation in error because you're correcting it periodically. These add some computational overhead, but it's usually not too bad compared to adding additional physics overall. And whenever you're dealing with structured data, like satellite imagery or weather station data that's always available at the same locations, it's pretty easy to set up your system to automatically integrate this information. This is a hard approach to do with unstructured data because you need to be tracking where it is and pulling it in. It's pretty complicated to design your filters in such a way that it works pretty seamlessly. You do have some issues, particularly in using remote sensing or aerial imagery, where now you could potentially correct your model backwards in the wrong way. For example, the drone or the satellite missed a detection, and that information is being fused into your forecast. So you're actually fusing in the wrong way. So you're decreasing the rate of spread when it should have been increased. Again, it doesn't really increase the accuracy much itself, more of a just correction as you go. And so it inherits all the same uncertainties associated with your base model. Another approach here, I think Chris was the first one to do this, is looking at, or at least in a systematic way, is inverse analysis. The general premise here is instead of actually correcting or directly assimilating the fire parameters, you set them as target values. And in this approach, you have some fixed parameters that are not going to be changing over time. For example, your elevation map or your slope or aspect. You don't think that's going to change over time. And then you have some free parameters. Typically, these are taken to be maybe a fuel model or a moisture content or a wind, things like that that are a little more uncertain. And then you use an optimization approach where you have some ensemble of simulations. You calculate the error between what the model predicted and what you observed at each of your time steps. And then you use that to determine optimal parameters for your forecasting model. A big advantage of this general type of approach is that if those parameters are constant in time, then you're potentially improving the predictive capability of your model because you're reducing input parameter uncertainty. So that's the main advantage of these. The difficulty there is we know, for example, weather changes over time. And so if you're optimizing on your weather conditions as your main factor, then it might not actually improve the predictive capability because you're not changing how you're predicting that weather. So how good it is really depends on how invariant those parameters are. You can also fuse inverse analysis with data assimilation approaches. So this was an interesting paper that came out fairly recently, 2019. Maybe that's just recent to me. But the premise here is that between assimilation windows, you are still making a forecast, and then you're looking at the perimeter, using that to tune your parameters, but then you're also assimilating the perimeter in to do a correction, with the idea that you are directly limiting your overall error, and you're trying to estimate the overall uncertainty in your forecasting tool so that you can reduce it. However, as you can see in the example shown here from the paper, that over time, the error was actually still growing over time. You see the slope, should have said this. In the Chan-VC similarity, the higher number is less similar, so worse. So you see the error is going up over time. And that slope is actually increasing, even though we're doing the inverse analysis and doing the data assimilation. I think I've already talked about most of these, so we'll just skip over the summary. Another big approach that's used, which is really in another direction, is let's see how much CPU power we need to throw at a problem in order to get positive lead times with a more accurate physics-based model. So there's been several projects that have focused on this. Most of them are using Wharf S-Fire. The case study here was done in Greece, and for the domain sizes that they were looking at, they found that if you were using about 200 cores, you could get a 24-hour forecast within 1 hour of real time. So that's pretty good. You're able to get 23 hours of a predictive forecast at the cost of 200 cores. So pretty reasonable. But this is still limiting the size of your domain and the complexity. So they're already making some sacrifices on the grid resolutions and such in order to actually get this to run in real time. The WarfX project is another similar that was using this type of approach. They used a more refined fire mesh, at least, which people have shown you really need to be modeling the fire. I think that's an error, actually. No, that's right, yeah. 28 meters to 33 meters for the fire resolution, and you really need to get down to that level of granularity when you're looking at these complex slopes and terrains in order to resolve the fire behavior, the weather interaction well. What they found in this was 4 to 6 hours of real time. You could get somewhere between 36 to 84 hours of forecast. So again, positive lead times, and again, they're using about 200 cores, which seems to be the magic number with current technologies. So big advantage, it's possible to do faster than real-time simulations using coupled fire atmosphere models. there are several limitations in that you do have to sacrifice on the size of the domain, both on the weather front as well as in the fire front. And that can potentially make it so that you're not really doing better on the rate of spread calculation, depending on the scenario you're looking at. Because of how expensive it is to run these, it also limits how many ensembles you can do. And so you can't really run with 10, 100, 1,000 different weather conditions because it doesn't scale well, because you need even more and more cores in order to do that. And you still have the limitation in that there's high uncertainty associated with the fire forecast in the empirical model itself. There's known limitations there for complex geometries, and you're inheriting all of that. All right. So the next technology that we're talking about is surrogate modeling. So the general premise here is that we can front load simulation time so that we don't need to run our simulations when a fire actually occurs. Instead, we generate a large database, and the simulations can take as long as we have computing capacity for. And you do a parametric study, come up with a range of parameters, and then you train a model that can make a prediction rapidly that will approximate that solution in real time. Key advantage here is that you can embed a lot of the physics and the parameters that are learned in a way that can be done in real time. I apologize if that's kind of small. That's really just showing the inputs that you would need for Farsight or Elmfire or any of those level set solutions as an input to a neural network, and then it's predicting the probability of fire throughout the domain. In that specific example, we weren't doing any recurrent operations. The model was basically predicting between satellite images and then correcting. But similar to the inverse analysis approaches and the data assimilation approaches, you can also incorporate additional time history of the fire behavior into your surrogate model. So what the authors here did is they took 10 previous time steps of simulation and included all of those into the model history in the model. And they were able to find that the surrogate model is able to reproduce the parameters with a reasonable effect. So the key advantages here are that simulation times are a lot lower. So when I was doing this as part of my PhD work, it was like 10,000 times faster than Farsight. You could run as many permutations as you want very fast. And you can also use this as a forecast in any of your data assimilation approaches. So it doesn't have to be used fully independently. But you have several key limitations as well. The main one being that every fire is different, especially in wildfires. So the question comes up when you've got these thousands and thousands of input parameters. For example, changes in topography everywhere, moisture content, fuel model, all those distributions. The question is, well, how do you actually know that the scenario that you're trying to model is within your training set? Because these models really do not do well with extrapolation. They do great if you're within your training set, but it's very hard to know if you're actually in your training set. And then another key limitation is with these approaches, you're inheriting all the uncertainties associated with the model used to train them. So your upper bound on accuracy is whatever the accuracy is of the model that you're using. Now, it still could be less than current operational tools. You know, if you were able to run 100,000 WRF S-Fire simulations and embed all of that into a machine learning model that could run faster than any of the operational tools, it may still be more accurate than those that can run real time right now. But people haven't really demonstrated that to this point. All right. So now we'll talk about some emerging concepts, some results that people have started to look at but hasn't really been fully flushed out yet. So these are really current areas of research. If you're looking for some interesting data-driven solutions, these are all areas to look at. So the first is, instead of actually training your machine learning model on simulation data, to train it directly on observations. We're just going to take all of our satellite data from history. We're going to trust that our active fire and burned area products are correct. And we're going to say, based on this observation, I want to predict what it looks like in the future. So it's pretty much the same neural network design as what you're using in a surrogate model. You're just changing the inputs to be satellite imagery traditionally. You might also still include some of the land fire data as well. The limitations you have, there's error propagation. Talked a little bit earlier today about active fire product, burnt area. They're not perfect. And so now your model's being trained on those products that are not perfect. You also have impacts with data availability. So again, we talked about this earlier with data assimilation. If you have fire parameters that actually grew pretty fast, but they were being occluded by smoke, you're now embedding that in your model when you're training. And so when you go to forecast, you're going to have that same issue. Another key difficulty with these, which I think is actually driving a lot of the uncertainties, is it's very difficult to actually characterize what humans did in the fire and all these legacy fires. You might be able to get it from incident reports and that kind of records, but it's very hard to get data on every hour for a wildfire exactly what was being done throughout your whole scenario. And the difficulty there is when you're training a model on these parameters, you're embedding active suppression efforts into how the model's predicting. And if those same efforts are not undertaken in a new scenario, you could be under-predicting how far it's going to grow because you're taking credit of something that's not actually happening. So if you want to do this, we really need to understand what fires, so this is where controlled burns and just fires that we know that there weren't suppression efforts on are really important, but you shrink your data set a lot when you apply those limitations. Also, a key limitation is you're generally limited to aerial derived information. So if there's something weird going on in your surface fuels below a canopy, that's really driving your fire phenomena. It's going to be really hard for you to capture that with satellite imagery because you're not seeing through the canopy. So there's potential in this type of approach, but it still needs to be flushed out a lot more before it's ready for operations. All right. Another approach that can be used, how am I doing on time? Yeah, we're good, is to use what's called physics-informed machine learning. So when I was doing this during my doctoral work, the general approach was in real time, we were simulating with a very coarse model. So we were embedding the conservation laws and the actual physical phenomena within the neural network because we're taking the outputs from that coarse model as inputs to the machine learning model. So we were bounding the error in the model because we were linking it to the physics at each time step. What we found is that the outputs from the coarse model, at least within the set we were looking at, were generally able to reproduce the thermal flow fields to a pretty good effect. I think I've got another slide on that. Yeah. So just showing an example here. There's a compartment fire. And you see on the left prediction is the neural network's prediction of temperature and then 3-component velocity. The center is showing the CFD prediction in FDS and showing the histogram of error. All the contours are scaled the same. You can see that the approximation is very good overall. This was all test data, so it wasn't used in training the model, but it was developed from the same set of parameters, so we're very clearly not extrapolating. So people haven't used this type of approach much in wildfires. There was a paper published earlier this year that started to use a slightly different approach. This is what's called a physics-informed neural network. What happens here is traditionally in your loss term in a machine learning model, you're just saying, this is right, this is wrong, calculate the difference, and then you propagate that error back through. What happens in a physics-informed neural network is you replace the prediction you're making with a specific state variable, and then your loss function becomes a conservation law. So you may embed continuity or something if you're predicting your velocity state, and then when you're training the neural network, you're saying, I want to minimize the error in this term as well as the direct prediction between the two. It gets pretty complicated. Lots of different approaches to this that people have used in turbulence modeling and kind of other areas. Traditionally, these are trained on a specific scenario. So what people do is they'll take PIV measurements in 2D and they'll train a model like this and maybe have point measurements at other locations and try and reproduce a full 3D flow field for a specific case by embedding the physics in the model. Kind of works. but people have done that. They've also looked at just measuring points within a flow field and doing the same kind of thing. But this paper did start to look at approximating the level set solution. So in this case, the level set solution was the conservation equation that was being embedded in that neural network for the loss term. And the authors found that the results were pretty in line with what you get from the level set solver. But they only really looked at a few of these kind of ellipsoidal, very homogeneous fires in these cases. All right. And the last kind of emerging topic I want to talk about is on model validation. In the wildfire community, it's been very hard to get good validation cases and to get everybody talking about the same validation cases to use. FDS, we've started trying to do this. There's 6 experiments in the validation guide of FDS, and we quantify the performance of the model in predicting rate of spread using the solution. A lot of scatter in the data, but going forward, making sure that the community is contributing to a common data set where we're collecting fire perimeters and collecting all this information so that we're all working in the same data sets for validation is going to be important. All right. So just some final thoughts. Lots of approaches exist for faster than real-time simulation, but it's very much not a solved problem because all of these approaches have different pros and cons. There's lots of ways that you can use data to improve operational forecasts. We didn't talk at all about using data mining of remote sensing to update moisture contents or fuel models or any of those kind of technologies. People have done that kind of stuff as well. But if you can think about it and think creatively about why are we doing things the way we're doing now, and how can we use data to better inform these, the sky's the limit for different ways that we can really improve things using the data. Just some ideas here. We need accurate data collection because if we're trying to use data, it doesn't matter if the data is not good, we're never going to really improve the state of the art. And we need to have these common databases. And last kind of food for thought is we're always going to be developing better models that take more CPU power. Scientists, whenever someone gives you a faster computer, you're going to find some way to use that to improve the model or do something. But I think that's where these surrogate models can really come in, because as computing power increases, algorithms improve, we're going to want to incorporate more physics as well. So even though we can always improve the physics-based models, I also see a need for these surrogate models because you're always going to want to do more with your model. All right, so that's all I have for today.
Session is open for questions.
Thank you for your presentation. So let's say like I have a zero knowledge in machine learning. So how difficult or easy to know learning machine learning?
Whenever you're getting into a new field, there's always a learning curve. I actually never took a machine learning class myself, but I was far enough along in the PhD and I had a background in statistics that I was reading textbooks and attending kind of webinars, lectures, things like that. I was able to pick up the fundamentals pretty well through that. It's the more you branch out, the more you learn about new topics, the easier it gets to get into another topic. So if you're interested in it, say get started. The easiest thing to do, you're never going to be good at it if you don't try. Right here.
Okay, yeah, thank you for the presentation. So the physics-informed neural networks seem like an interesting avenue to go down. I was wondering whether you could maybe do the opposite as well and have the neural network output potential physics to be then used in the submodels that are in the more detailed.
So there are approaches. There are approaches that use that. It's typically not neural networks. What you're talking about is, what's the term they use? Symbolic regression is typically what's being used there. And basically what you do is you define functional forms, so exponents, logs, addition, multiplications, and then you give it data and some target output, and you say, apply these operations to the data in whatever way you want and get to this result. and then you'll use a genetic optimization to try and figure out the functional form. Those, I've played with them, they don't work well. You can seed them with a starting point and then get some meaningful results out after that. But if you just give it raw functions and tell it to do something, you're going to waste a lot of time.
I guess it becomes ripe for the wrong reasons.
Yeah. Mm-hmm. Over.
So in your physics-informed machine learning, is it both? It is trained for a specific type of flow field and temperature field. So how easy it is to adapt it to other type of flow field or temperature field?
So that really depends on how you design the model. The way that I designed it in my doctoral work there was basically designed to any compartment fire in certain ranges of aspect ratios, certain ranges of fire sizes, and I ran thousands of FTS simulations to build that database. And I found as long as you were within that same set, it was okay. You could actually, I think in the paper on this, I put together multiple rooms. I trained on just 2-room configurations, but I put together multiple rooms and like full assemblies. And it actually did a pretty good job predicting in rooms that were further away from the fire. So it was able to learn robust features, but it really depends on how big of a parameter set you're looking at.
I'd like to point out that this problem is not new, though. I mean, I think it's shedding a new light with artificial intelligence. But if you look at the zone model, that is one of the main tools that was developed in the 1980s, these zone models are based on correlations that typically assume that the fire is well ventilated. And so, so that means as long as you are in this domain of validity of well-ventilated fires, the zone models are very good tools. But then when you go to underventilated fires, every one of these correlations breaks because the fire was assumed to be sitting above the fuel source. And so, that's where you need to go to CFD to adapt to these new regimes. So the fact that these tools have a limited domain of validity and you interpolate rather than extrapolate is a standard problem.
And the key there is to really quantify what does it mean to be within your training set. And to do that, you need to have a validation basis. And some of what I looked at in that paper was looking at calculating a root mean squared difference between all my input parameters and everything in my training set to see kind of the minimum distance. If you took every parameter and had it as a different axis, and you're basically looking at what's the closest you are to the convex hull of the training set. And it worked pretty well. I was able to kind of look at how the error performed based on where you were within that set. But there's not really a good systematic approach to that right now. Yep.
Questions? Maybe I can ask one, because in your conclusion, you correctly point out the need for data. So if you are doing physics-based modeling, you need data for validation of your models, but if you are doing machine learning algorithms, you need data for training of the algorithm. And so the question becomes, where do we get this data from? And it a little bit looks back, in my mind, to the presentation by Ivan for wind and fires. We don't have a lot of data. We have data that are typically limited to laboratory scale experiments or prescribed fire experiments, but they tend to be under mild conditions. And then the question is whether you can extrapolate to mega fire situation. And there we don't have a lot of data. So do you have any insight of how we can find this data?
So there's a few tricks with data, and they all have limitations. One is to perturb the data in some way and to kind of expand the data set a little bit, rotating it, things like that. It doesn't really embed too much additional, but it gives you a little bit more. You can also, this is something we've tried to do, minimal success, but to use both real data from collected as well as simulation data. In compartment fires, that works pretty well. But in wildfires, you can't get full field maps of moisture and things like this. And so you have to make some assumptions on how to correlate your satellite data to model input parameters, just like if you were trying to model the scenario. But I think coming up with better ways to get model inputs from satellites and other remote sensing technologies will be important, because then that allows you to use both real data and simulation data so that you can do that augmentation effect.
Right. So about simulation data, it looks, as a computational modeler, when I want to publish something that is numerical, the reviewers always challenge me, bring me some experimental data to compare with. And it's very hard to publish if you're not doing this. And however, we see, because of the needs for a large amount of data for artificial intelligence, that we see some people just relying on FDS simulation or numerical data to actually train algorithms and go from there. So there is no real check of whether this is an approach that is validated by comparison with experiments. Mm-hmm. So that's one clear way of trying to fix the problem of not having enough experimental observation. Mm-hmm. But is that, are you worried that this may be taking us to an abstract world where we are losing sight of what the reality is because we don't do these reality checks? Or is that something that is legitimate as an intermediate step, or how do you view that problem?
So I think it's both. Whenever you get tools that are easy to use, there tends to be a less understanding because there's a lower barrier to entry with those things. But that's true of FDS as well. FDS is being taught at undergrad levels. If you wanted to run FDS simulations 10 years ago, you had to really know your stuff because it was not very easy to use. Now, it's a lot easier to use, and so there's less understanding associated with the physics-based tool. And you do get the same in machine learning. I do agree there needs, especially if you're going to make a tool available to public and anyone to use, there needs to be a higher degree of quality standard on it in terms of the progress. There was a recent paper that came out that built on the compartment fire work I did here that if you go to, I don't remember the website, sorry, but they basically took Atrium or Atria, and they used different fires in the center or the side and different exhausts from the ceiling, and they looked at smoke filling with depth. And they just have a public available website. You can go in, put your fire size, your room size, and you can get kind of a video output of what your smoke layer depth looks like with time. So there's absolutely zero validation that they actually modeled a realistic atrium, but it's available. And so to me, that's very scary because people could be using that to design their smoke exhaust systems. And there is no validation basis that the actual models they trained on are correct.
Alex first.
No, go ahead.
Okay, thank you. So, and we're getting in the territory of this afternoon, so I'm going to try to be brief. But I think what you showed in your presentation is that there are advantages and disadvantages in every approach, and so I wanted to comment on what you were saying, Arno, and on your response is that we always need an experimental validation, at least to know how the model will work in a certain range. Now, if we're in this range where we'll build confidence in the model, and I'm talking about more physical models, so we use the physics at this level, then we can use the model to interpolate in this range and generate more data that can be used to train the other models. The problem is very much when we try to extrapolate to things we don't know. For instance, in one of your slides, you were talking about the empirical models, but some empirical models, and in Australia, for instance, the MK, different 1 to 5 or 6, they do a very good job, even for fires in eucalyptus forests, because they're in a limited range of conditions. But if people take them and want to do that, for instance, for a fire in Portugal or in the US, then we're trying to use the tools outside of their range, and then we have a problem. So we need the physics, we need the experiments, and then we can train the other models to maybe perform better.
And just to add on that, that's where it gets really important to understand how can you quantify in a statistically significant way, are you within your training set or not? Yeah. And there's just not been a lot of good research in that.
That's a big gap.
Yeah, I want to expand exactly on what Albert mentioned, because I think we have the potential to completely miss the scope creep transition from FDS being built for indoor fires initially and being migrated to the outside. So if you look at the validation data set, 99% is indoor related, and we have a very, very small, it's a sliver of data. I mean, if you look, it's really the Australian grasslands and the Camp Swift stuff that we have done. And these are all very benign conditions. So not only we're taking the model outside, we're introducing now a large number of parameters, topography, weather, fire, atmospheric interactions, etc. But also we're completely missing the part that the conditions for this limited data that we have are completely off scale compared to the real events. So I think using a tool to build other tools has to be done very, very mindfully, as you said, because you can run a million different types of simulations in FTS, but if only one fraction of 1% are validated, then the potential uncertainty that you then use and infuse into your machine learning is going to just explode. So I think the fact that we have tools shouldn't by default imply that we can use them everywhere. As Arnaud said, I think we have to be very mindful, and as the tools are getting easier to use, we have to be very more mindful to let the next generation know that there are a lot of limitations.
Right. Actually, just before we go to your question, but this issue of defining the domain of validity of the models that we're using is something that we don't do very well as a community. There is nowhere an explanation of, like, going back to the zone models. Zone models should only apply to well-ventilated fires, not to unventilated fires.
Exactly.
There's nothing that says that.
And not tall, because they don't work well for tall spaces either.
Yes, please.
Yeah, so since having the perfect model via the enabled by AI data-driven approaches, since this is far-fetched, can we use AI to improve some inputs, like the fuel models, for example? For me, personally, I have not understood how well we even describe the flammability of the terrain, for example. And I assume that combining the remote sensing technologies and AI, we can at least have a deep dive, describe this very well. What is your view on that?
So a lot of people, the area that's seen a lot of that for real-time stuff is using NDVI, that's Normalized Difference in Vegetation Index. There's other indices as well, but they've tried to train machine learning models to take that and figure out your different moisture contents that you need for wildfire modeling. They work in some areas, they don't work in others, and the scatter on it is just very high. But I think there is a place for using machine learning to help derive some of these parameters. But the difficulty there comes in that remote sensing is an unclosed problem because you can't see everything with remote sensing. And so the question becomes, what kind of data do you need to collect in order to do this reconstruction well? So that's what would be a very interesting study is, if you were going to put weather stations at what frequency or where do you need in situ places in the ground, and how can you fuse all of that together to get better model predictions? I think that would be a good systematic study, but also a really pricey study to run. And so you've always got that balance when you're talking, let's collect a lot of data, where there's only so much you can do in budgetary constraints. So.
Right, so we're going to close that session. Let's thank Jonathan again.